Great. All right, a little bit about me. My name is Sarah Marquise. I am the Research Data Manager at FASRC Computing, FAS Research Computing, and I collaborate with faculty members, researchers, and staff to better manage their research data throughout the data lifecycle. I also offer consultations and trainings on topics such as data storage, data organization, and data sharing techniques. We develop data management resources and tools that can help you track storage usage and prepare your data for sharing and reuse. And lastly, I've also been working with a few vendors over the last few months to develop and refine data transfer processes that can help researchers with data cleanup efforts and migrating data through the life cycle from active to long-term storage. So in today's session, it's a 1-hour training session. So I hope to cover a few different topics related to research data management. We'll go over an overview of what research data management is and why it's important and how you can move your research data throughout your project lifecycle. I'll highlight some data management policies and procedures, including those that are specific to Harvard. We'll review some data organizational techniques, how to make your data more discoverable, while also adhering to data management and sharing plans. And I'll talk about those in more detail. We'll discuss how to improve your data analyses using different collaborative tools like RSpace, which is an electronic lab notebook supported by Harvard, and other third-party tools. I'll detail the various storage offerings that we have at FASRC, as well as some of the recommended workflows around data storage, data retention, data security, and data cleanup. I'll discuss various storage tools like data visualization tools that we have available to you through FASRC that can assist with managing your storage and cleanup. And then lastly, we'll discuss data sharing and reuse and why you should be considering using a data repository and how to make sure that your data is considered open access. So the National Institutes of Health define research data management as the process of validating, organizing, protecting, maintaining, and processing scientific data to ensure the accessibility, reliability, and quality of the scientific data for its users. So with this definition in mind, why is the act of research data management important? I've listed a couple of considerations on the slide. Essentially, good data management techniques can prevent your information from getting lost, misplaced, or corrupted. It ensures that your data is accurate and reliable, which ultimately can lead to better research results. It allows for easier data collection, organization, and cleanup, which ultimately could save you time, effort, and funding in the long run. It makes collaboration both here at Harvard, so internally as well as externally with collaborators, more efficient, cleaner, and you have more succinct data sets that are easier to understand and reuse. It increases the impact of your research, actually gives you credit for the work that you've done beyond your published article. Various funding agencies and publishers now require submission of data sets alongside those published articles. So overall, it's just good to think about data management as a good research practice. So when we're discussing research data management, it's always good to keep the FAIR data principles in mind. So these are principles that were published in 2016. They guide researchers on how to make sure that their research data is reusable, and it applies to a variety of digital research. So FAIR, F-A-I-R, stands for findable, accessible, interoperable, and reusable. So what does this mean for your data? So if you use these principles as a guide, you can ask yourself a few questions. Is your data findable or discoverable by others? Is your data easily accessible to others? Is it accessible from different devices? So is it in a format that would be accessible to everyone? And then is the data reusable? So does it contain enough context and information that it could be reusable by other researchers? The FAIR data principles usually come into play as you're finishing up your research project and you're getting ready to publish and share your data, but it is good to keep these principles in mind throughout the project, especially at the start, so you can better manage your data and adhere to this framework later on. I'll go over these concepts in a bit more detail throughout the slides, but I do suggest that you keep this simple acronym in mind as we make our way through the presentation, and just think about what state your research data is in and whether it would qualify or be considered fair. So we've talked about the act of research data management, but what is research data? Like, how can you actually define it? So we can define scientific research data as the recorded factual material commonly accepted in the scientific community to be of sufficient quality to validate and replicate research findings, regardless of whether that data is used to support scholarly publications. So that's very broad terminology, but essentially it's any research data that could be collected, created, or acquired throughout your research project. It may result from projects that were conducted here at the university or on Harvard property. It could be developed or collected under the direction of the university, even if those research activities are happening elsewhere. And it could be data collected with university resources, such as equipment or funding. Also, it's good to keep in mind that Harvard does have ownership over all research data that results from projects that were conducted at the university or using university resources. And I'll talk about that policy in a few minutes. So the research data lifecycle is a representation of the different project stages, from data creation to publication, and then how it manipulates associated research data. The lifecycle begins with planning and design of your project, followed by data generation and data analysis, data storage, so storing your data throughout the project, preparation for data publication, and then finally, hopefully, data sharing and reuse. Although your project might not follow this exact course or even move fluidly from one stage to another, there may be instances where you'll have to reverse course or reanalyze a data set, or maybe acquire new data sets from an outside entity. But in general, most research projects are going to follow this similar path. The data management activities are also going to vary by discipline, institution, and research project. So this just makes offering data services at a broader level, at a university level, a challenge. There are many different types of data that are generated at each stage of your research project. Source data, or raw data, is the data that has not yet been processed, modified, or analyzed. Your project's raw data could derive from an instrument, or you might have acquired it, so you might have downloaded it from a shared database. During the data processing, the raw data is then cleaned, sorted, and filtered to reduce the number of unnecessary, inaccurate, or redundant fields. This step is especially important. I think oftentimes we kind of gloss over it, but it really is an important step in order to ensure higher quality results and can help to streamline your data analysis. Data analysis is the process of inspecting, cleansing, transforming, and modeling data with the goal of discovering useful information, informing conclusions, and supporting your decision making. The data is then published alongside your scholarly work. In the last decade, it's become increasingly common for researchers to make their data available to others once they have completed their projects. So now that we understand the process of research data management, we have a better understanding of what types of research data exist and how they are involved in the research data lifecycle, and why it's important that we engage in research data management. We should review some of the data management policies and procedures that apply here at the university. We'll talk about how to draft a data management and sharing plan, which is required by certain funders. We'll talk about roles and responsibilities around managing data within your group or lab, and then how to organize your data, including file naming conventions and directory structures. So I do recommend that you be cognizant of any existing lab, department, or university policies and procedures around research data management. There are several institutional policies that I've listed here on the screen that you should be familiar with, including the research data ownership policy. This is the one I kind of mentioned in a previous slide that just states that the university is the owner of all research data produced and analyzed for projects at the university. The policy also stipulates that your PI or faculty member is ultimately responsible for maintaining that data and is considered the data steward of the lab or group. We have the Harvard Research Data Security Policy that provides guidance on how to keep your data safe and secure. This is especially important around any confidential or sensitive data. If you have data that has any PII or private information, you'll want to make sure that you adhere to this policy. We have an FAQ around data retention. This just is a general institutional policy that stipulates that any essential research records need to be retained for a period of no fewer than 7 years after the end of a research project or activity. There are also several funder policies that you should be aware of, especially those related to the NIH and NSF. There's also guidance from the GDPR or General Data Protection Regulation that has to do with data that's acquired through the European Union. Also, I do want to mention, I should have mentioned this at the start, we will have time at the end for questions, but feel free to post any questions you might have in the chat. And then we will stop the recording at the end of the slide deck, and then we can actually have a question and answer session. So again, feel free to post in the chat if you have any questions, and I will make sure to get to those at the end. All right, so moving on, a data management plan, or a DMP, is a formal document that outlines how your data will be handled during or after a research project. Many funding agencies, especially government sources, will require a DMP be created as part of their grant application process. Even if you're not seeking funding through some of these government agencies, just having a plan for your research data is considered a best practice and can help you comply with all these different policies for responsible data management. Funders will expect the data management plans to be updated frequently throughout the entirety of the research grant. So you may need to alter the document over time in order to reflect any changes that have happened since the project started. So for example, in the DMP, if you originally stipulated that you were going to store your data in a tool like Google Drive, and then due to the data type that you generated, it doesn't comply, or you can't put it in the Google Drive folder and you had to move it somewhere else, you just would want to notate that in your DMP that the storage location has changed. In order to create a DMP, Harvard actually offers an online template that you can use in a tool called DMP Tool. This is a free open source tool that actually we have a license through Harvard Library, and you can utilize it to help draft that DMP. We also provide Harvard specific guidance on how to draft and submit a data management plan in the DMP tool. There are other templates available for various funders like NSF and NIH, which have varying requirements. So it's a great tool that I recommend everyone utilize if they do have to draft a DMP. So roles and responsibilities. Data management responsibilities extend beyond just your PI, even though they are the data steward for their lab, or even the researcher who initially created or collected the data. There are various parties that will need to be involved in the research process and can play a role in ensuring the quality of the research data. It is essential, however, that these roles and responsibilities are clearly defined and assigned rather than assumed. Identifying specific tasks and responsible parties is going to help with budgeting, implementation, and preservation of your research data. I do recommend that for every group or lab that you have at least one individual who could be considered a research data manager. This is just an individual who can act as a primary contact between FASRC and the lab and could take on some other responsibilities like promoting and supporting data management best practices, organizing folder structures, and maybe establishing a file naming convention, or identifying data that could be moved to long-term storage and working with FASRC to make sure that data is moved to a long-term storage option or even deleted. So moving on to data organization, a tangible way that you could see immediate improvements in your lab's data organization is by implementing consistent and streamlined directory structures. For your folder structure, I do suggest that you arrange your files hierarchically or the idea of nested folders, so folders within folders. You would put each project in its own directory, name that folder after the project, ideally keeping it to less than 32 characters, and include a combination of the project title, a unique identifier, and maybe the date. Next, establish a folder hierarchy that would align with your project. So generally, this would be set up so that you have folders and files based on attributes and keeping similar items stored together. This is a very familiar and widely used organizational structure. It's also good at representing the structure of information and the files that were generated throughout the project. So an example of this project structure or the folder structure is there on the slide. You have a top folder for the project and then subfolders for data, code, and documentation. You can also see there that the data folder has been divided into raw and processed data, so data type. It is good practice to keep your raw data separate so that it's not modified or lost. And it's as soon as you manipulate the raw data, you'll want to create a new folder as it's no longer raw, it's now considered processed data. While there's no ideal system for your folder organization, I think the one that we have here is a good option, but the best one is going to be the one that works for your research project. Within each project folder, I recommend that you record all information that would be needed to interpret the context and content of the files. Sufficient documentation often determines whether those older data sets could be reused, especially if the context is lost over time. So if an individual who created the files has now left the lab and there's no additional information provided or no contextual information included in that folder with those files, you might not know what the files are or how you could reuse them in the future. Documentation is an ongoing process. It should occur throughout your project rather than a one-time effort, but it can be created in a number of formats depending on your research workflow. Options could include a paper notebook, an electronic lab notebook, a README file, code books, or data dictionaries. On the screen is a nice example of a project README file that was created by Cornell University. It's just a flexible text file that provides additional context around the data sets, and it is included in the folder with the data itself. A good data practice is to store, like I said, that README file in the project folder, explaining things like file naming conventions, maybe abbreviations or codes that are used. Maybe you are generating data with an instrument, so you might want to notate the software used or why the instrument, labels the files in a certain way. So all that contextual information can be included in a simple text file and then stored in the folder with the rest of the data. If you're expecting to deposit data sets in a data repository when your project has completed, the repository may ask you to provide a README file with all this additional information. So just keep that in mind. Creating this README file at the beginning of your research project and then updating it consistently throughout your project might be easier than having to do it retroactively right as you're getting ready to publish and share. Again, no matter the format, there just should be enough detail so that another researcher could pick up your work, pick up the folder, and understand exactly what's inside of it. I do recommend avoiding any proprietary formats though, like a Microsoft Word document or an Excel spreadsheet. Instead, try and go for a more open format like a CSV or a text file. So similar to the establishment of well-defined directory structures, having enhanced file naming can significantly improve the searchability of your files. A decent file naming convention would include key pieces of contextual information about the file that could make it easier to visually or digitally scan, and you can immediately discern the contents of the file just by looking at the file name. Some general recommendations for establishing a file naming convention for your project is maintain the same file names throughout the project. It's even better if you can get the entire lab on board and have similar file naming conventions across for multiple projects across the lab. Describe what the files contain and how they're related to one another. Include any useful information like date, project title, and then when working with lots of files, file versioning can really be important. It can ensure all members of your project are up to date on the various versions. You can capture the version of the file in the file name by including things like V2 or V3, but do steer clear of any confusing terminology like final or draft. You can also use file sharing platforms that have built-in version capabilities like Google Drive or Dropbox. They keep track of the versions for you. Again, just determine what information is vital to the project and the data set, and then build out the file names from there. They will differ depending on the needs and workflow of your research team and project. All right, so as we make our way through the research data lifecycle, we're now moving from data planning to data creation and analysis. In this section, I want to highlight a few useful collaborative tools that you can use that can help improve your data workflows, and then we'll talk a little bit about data transfer processes. So the first tool is RSpace, or Research Space. It's an open source electronic lab notebook, or an ELN, and it is supported by Harvard IT, and it can help researchers organize, store, and share protocols, analysis, and experimental notes in a centralized and secure platform. Tailored for academic environments and the research workflow, ELNs can help manage and track research data throughout the data lifecycle. They facilitate good data management practices. They can support data review and oversight. They enable collaboration, and you can manage things like samples and other inventories of equipment. Open Science Framework. This is provided from the Center for Open Science. It's a free and open source project management tool that can help you throughout your project lifecycle in following open science best practices. So it promotes open and centralized workflows. It enables capture of different aspects and products of your research. It's a flexible repository, so it can store basically anything: research data, protocols, documentation, materials. I actually use Open Science Framework for a lot of my presentations and conference resources and documents. So it's a really great centralized location that you can store a lot of these materials that are generated as part of your project that might not be considered published works. And then there's GitHub. GitHub, everyone knows, is a web-based service for Git repositories. It's commonly used for managing and sharing different versions of code for your project programming projects. One thing to note is this is also an open source tool. It is not hosted by Harvard. So if you do have information in GitHub, just make sure you have an additional copy stored somewhere else, because it is a third-party vendor. You just want to make sure you have an extra copy of your materials stored somewhere else in case anything happens to GitHub. So some data transfer tool options. Transferring data between research platforms is often very challenging. I wanted to quickly list a few tools that you can use with data transfers and how to select the tool depending on the size of your data set, data security level, and who's going to need access to that data set. So a tool we use a lot is called Globus. It enables file sharing with external collaborators. You don't need a FASRC account to use it. And it's really useful for, again, like I said, external collaborators. So if you need to transfer data to another institution, Globus is a great tool to use for that. It's online, so you just have to upload information to the online platform. We have a lot of resources and documentation on our website if you're interested in learning more about Globus. rsync is a fast and versatile file copying tool. The great thing about rsync is that it migrates only modified files from the source to destination. So if something happens mid-transfer, it's not going to start all over and try and transfer your entire data set again. It will only migrate files that have been modified. FileZilla is an open source client. It's great because it's available across platforms, so you can use it on Mac, Windows, Linux, etc. And then there's rclone, which is a convenient and performant command line tool for transferring files and synchronizing directories. And you can actually use it to sync between FASRC file systems and other tools like Google Drive. Data storage. So data storage, we will review recommended data storage workflows. We'll talk about migrating data from active to long-term storage, what some of the rules are related to data retention and archiving, what data storage options are available to you at FASRC, how to keep your data secure and backed up, and then at the end of your project, how you can start engaging in data cleanup efforts. I'll also review a few data storage tools that we've developed that can help you with better managing your storage usage. So similar to the creation of a data management plan at the start of your project, it is helpful to create a data storage plan, just outlining how you are going to be storing and organizing your data throughout the project. To help get you started, I've developed some questions that you can ask yourself related to data storage that could be noted in a data storage plan. So, where will my data be kept throughout the project? When and for how long should my data be retained? Different institutions and granting agencies will have regulations or recommendations about how long your data should be retained. You will need to keep all these policies in mind when you're deciding how long to store your data. What other data types will you need to store, like code, documentation, or protocols? What formats will you be saving your files in? Again, I recommend using interoperable formats, so formats that are not software dependent. These are open and unencrypted. Again, the example of a text file versus a Microsoft Word document. So once you've thought through some of these questions in more detail, you can notate the answers in a quote unquote data storage plan. Again, it could be as simple as a text file, or you could even incorporate this information into your existing lab documentation, just somewhere that it's easy to refer back to, or you could even point new lab members to as they enter or depart the project. Just having this information already compiled and available for review is going to help streamline that onboarding and offboarding process. So how your research data is going to be utilized and accessed is going to help determine where that data should be stored. Similar to the research data lifecycle, you're going to want to think about lifecycling your data through a storage workflow, moving your active data through this workflow until it reaches long-term storage. So as you begin to generate or acquire raw data, you'll want to store that data in an active storage location. It's readily accessible, and you'll be viewing the data often in order to analyze and process it. Soon after you generate or acquire raw data, you will then move it to a more intermediary location so that the raw data remains protected and separate from your analyzed data. Once your data has been analyzed and you're no longer frequently accessing or modifying the data, it could then get moved to a long-term storage option. Data that should be moved to long-term storage includes any data associated with published data sets, data associated with finished projects, archival data, or data associated with lab members who are no longer with the lab, and nobody in the project is using that data any longer. And then after your project is completed, you'll want to evaluate the data set to determine whether it should be moved to long-term storage, destroyed, or archived. Many institutions, including Harvard, have an archive or special collections unit whose mission it is to collect, maintain, and provide access to records of enduring value for historical and research purposes. And this does include research records and data. Records eligible for permanent retention may be those that document a breakthrough, or maybe they were generated by a lab or individual who had a great impact on their field, or maybe it's a data set that's highly reusable for a particular area of research. All of those records would be eligible for permanent retention in an archive. And it's important to make the distinction between archival data and long-term storage. So the permanent retention or archiving of data is often a significant investment for the institution. It implies the ongoing migration of electronic format and storage costs, as well as care, maintenance, and access services for the records, often in perpetuity. So most research data and records will not fall under this category. Most research data and records will just need to follow the retention policies. For example, the Harvard policy is 7 years. You're not required to keep your data for longer than that retention period. Often the cost of long-term storage is prohibitive for researchers, and so you might not be interested in storing or maintaining data for longer than necessary. Should your research data not meet the criteria for permanent retention or archiving, you may want to take steps to ensure that you're safely and completely disposing of the data once it has met that specified retention period. Disposal of research data might include deleting, swiping, destroying, or otherwise disassembling any materials that are holding data in a way that ensures the data cannot be reconstructed or extracted. Again, check with the policies of Harvard, but also with your funder to make sure that destruction is in line with their policies. Sometimes there are different policies that might apply to research records, but not to data. So it's good to be confident in the policy before you take steps to destroy anything. And then if you are going to destroy any data, just make sure to create an inventory of what you're actually disposing of and include things like format, dates, any other relevant information about the project, and then a reason for the data's destruction. This is just going to make sure that you have a sufficient record of your activities. All right, so we've briefly discussed data retention, mostly in relation to the Harvard retention policy. But for additional context, data retention is the length of time that data needs to be kept in order to meet funder requirements or institutional policies. So understanding data retention is going to really help with your budget planning. So if you know you have to keep your data for 10 years in order to meet your funder requirement, then you'll have to include that in your initial grant submission, saying that you'll need X amount of money in order to retain data for that 10-year period. The retention period is going to differ based on your funder, your state or federal guidelines. Ultimately, the retention is going to depend also on the type of data, the purpose for which the data has been collected, policies of funder agencies, such as the IRB. So if you have to work with the IRB related to your data, maybe there's intellectual property restrictions, maybe you have human subjects data. So all of those factors are going to affect your retention period. However, data retention policies only apply to essential research data and records. So that's data that's considered integral to substantiating grant applications, published research, or patents, or records considered for permanent retention. There are a list there on the slides of what an essential research record is. Again, it's records associated with grant applications, records needed to substantiate compliance with sponsored research, any records associated with published research and patents, scholarship considered for long-term preservation by the archives, or data material or materials designated as essential by your school or relevant disciplines. So any research data that falls outside of those requirements, those stipulations, is not considered essential and therefore does not fall under the same data retention policy, and is eligible for deletion. So I mentioned archival storage differs from long-term storage. Most people use these terms interchangeably, but they're technically two different types of data storage. Long-term storage is the storage of research records to meet those retention requirements, and archiving is the permanent retention of research data for reuse by other researchers. In order for data to get archived, they will have an appraisal process, so you will actually work with an archivist who is skilled in records management, and they will review the data sets and then determine whether it is archival worthy, and then they will work with you to actually permanently retain those records. For data to be retained permanently, there'll need to be clear ownership, and the data will need to be comprehensive or have some contextual information. So the percentage of data that's actually archival is quite small, again, due in part to the costs and care required to maintain those records. So there are a couple of questions on the screen that will kind of help you better understand when appraising your own data, if it could be considered archival. Okay, so now that we understand how to migrate data through that data lifecycle from active to long-term storage, based on how you're using the data and who needs access to it, we can review the various storage offerings that we have here at FASRC. So we have our cluster storage. This is a high performant location. It's a high performance storage. It doesn't have backups. It's really designed as location for data analysis because it has really high read and write speeds. This is connected to our high performance compute cluster. So you should be putting your data analysis here in this location. We have our Isilon lab storage. This is ideal for general file sharing, general lab storage. I do recommend it as a primary storage location for your lab documents, as it does maintain backups. So you could also use this space for your raw data sets, because again, it has another copy in case anything happens, and it keeps your data separate from your processed data. We have a lab share. This is a less active storage location for lab data. It's not really designed for high throughput jobs. It has lower read and write speeds, but it's another storage option you can use for your lab documentation, and it's a bit cheaper for you to utilize. So we have some labs that like to use it for their less active storage. And then finally, our long-term storage option is tape for data that you need to keep to meet those compliance requirements, your institution retentional requirements. You can move your data to tape. The data is not accessible. It's really should be for your finished project data. You won't be able to immediately retrieve the data. So just keep that in mind. It really is designed for the long-term storage of your data. And then we have our FASRC cluster, which is a secure cluster environment provided to researchers that need additional security for their data sets. It's a secure enclave for data analysis for data sets that are considered level 3. And I'll talk about data security in a minute. So data security. The type of data that you're working with is also going to dictate your data's security level. So where and how your data needs to be stored or handled. Understanding data privacy and security requirements is necessary to secure your sensitive and personally identifiable information. It's a fundamental obligation grounded in the values of stewardship, integrity, and commitment to your original data source. Most institutions have security levels for their research data. Harvard has a multi-level security system, so we have 5 data security levels that indicate what tools and platforms you can use for each data security level. Level 1 is publicly available or unrestricted data. So examples of this would be public repositories or consumer products, anything that's available online to the general research community. Level 2 is unpublished, non-sensitive research data. This is, for example, anything that you put in your standard email. It's most of our storage offerings are level 2. So it's any unpublished, non-sensitive data. Level 3 is sensitive data and some regulated data that could be damaging if made public. So some storage options for level 3 include Harvard Dropbox, OneDrive, SharePoint. All of those can house sensitive data level, and including our FASRC environment as well is up to level 3. Level 4 is for sensitive data that could place the subject at significant risk if the information is made available. There are very few storage platforms that will hold up to level 4, but some options include the Harvard Secure Transfer and maybe an external hard disk with encryption. So examples of what level 4 data would be is maybe HR information like social security numbers, addresses, anything like that that would make an individual, it would put an individual at severe harm if it was made available. And then level 5 is very sensitive data. We hardly ever deal with level 5. Level 5 is like Department of Defense data. It's very, very secure. And it actually requires additional security consultation with Harvard IT in order to deal with level 5 data. So in terms of security related to backups and prevention, so one straightforward data security strategy that I do recommend is called the 3-2-1 rule. This rule stipulates that you should be retaining 3 copies of your data on 2 different types of storage formats, and one of those types should be offsite. So for example, if you wanted to maintain a copy of your raw data on your lab computer, then that lab computer should ideally be using CrashPlan, which is a backup software that we support here at Harvard that would back up your files to a cloud resource, which is offsite. And this would prevent total data loss due to any localized events like fire, flood, theft, things like that. Just making sure that your data is spread out across multiple types of storage. It's going to diffuse the risk if your data is lost or anything happens to it in the lab. While it's important to think about data retention and long-term storage, it's equally important to think about data deletion and cleanup. So a significant issue that we have here at the university is the accumulation of unnecessary or duplicative data sets that are long past their usefulness. We do recommend connecting with your PI or group leader to discuss what data actually needs to be retained and what data sets can be removed. Duplicative and dispensable data sets should be removed to reduce any strain on your group's storage usage. Also, make sure to place any data and documentation in a group folder. This ensures that any important files and data are not lost when lab members leave. Group folders keep all shared data under the group's control and provide continued access and preservation of that data for ongoing projects. It's also imperative to think about data cleanup when lab members are preparing to leave the lab or even the university, and should be integrated into your lab's offboarding procedures. So here are some recommendations that I make when it comes to offboarding. I do recommend reviewing and organizing your research data and documenting where everything is stored. You can also add additional context in a README file like we talked about at the beginning of the presentation. Back up and move any of your personal files from your local computer or maybe a local Dropbox or local Google Drive and move it to a group storage location. Confirm that those files are accessible by your PI or group leader before you leave. And then transfer any folder or website ownership to remaining group members. Identify data that could be deleted or moved to long-term storage, and just confirm with your PI that the data can be deleted or moved. Store your lab notebook or other lab records somewhere where they're accessible by remaining group members and collaborators. And then if you do want to take data with you, if you are leaving the university and you're still kind of working on your project, or you intend to take some of your work with you when you leave, you do have to consult with your PI and get approval from the university before you can remove data. Again, because Harvard is the owner of that research data. And so you need permission from the university before you can leave with the data sets. So here are a few examples to demonstrate kind of what I'm talking about in terms of offboarding scenarios. So you have a lab member who's leaving the lab and they accidentally or intentionally removed some of the data. Perhaps they did get permission from the PI to take the data with them, but they didn't inform the lab exactly what they were going to take. So there's some ambiguity there. Another issue occurs when data is kept on a personal computer or cloud account, like a personal Dropbox or personal OneNote, and then it's removed or wiped when the lab member leaves the institution. I actually had a lab where this happened, where the lab member was storing something in a private OneNote account on their computer. They thought it was shared. They left the lab. IT wiped the computer, and all of the lab notes were gone. So just make sure that all that information is available to your lab members before you leave. So to help with managing storage and cluster usage, we've developed a few storage tools. One is called ColdFront. This is an open source allocation management system that is kind of a central portal for maintaining and understanding your cluster usage and your storage usage. It enables the viewing and management of both your lab group and your allocation. So how much storage you have, or who is allowed to access your lab group. So it enables viewing and management of lab group storage, cluster allocations, so you can view and add members, you can adjust email notifications, you can request new storage folders, or maybe you want to modify your existing storage. So it's really great. It's a really great tool. It's available to anyone who's in your lab group, and it is on an online web platform. And then another tool is the Starfish Zone interface. This is a self-service tool that allows users to view their storage and all the metadata around their files. So you can actually navigate through your folder structures and access detailed information about your files, like who created the file, when was it last accessed, when was it last modified. All this information is available through the platform, and you can even export it to a CSV file. So this tool is really great for data cleanup efforts. I highly recommend it if you are looking at, the whole folder, lab folder, and you're interested in seeing, when was the last time somebody actually accessed this information and can it be deleted? Quickly highlighting data sharing. So the data that you share is going to vary based on your project and research area. However, enough data should be provided that would allow for replication or reproducibility of your project. If you've been keeping your data organized and documented throughout the project, then sharing your data should be easy. To publish data, we are going to need some sort of infrastructure that's going to help support this, as well as discovery and long-term accessibility of your data. And so this is the role of data repositories. The idea of posting your data to a personal website or storing it in a Google Drive folder and just making it available when people ask, that's no longer acceptable. A lot of the funders are not going to allow you to do that. They're going to require that you share your data in a repository. Repositories provide the technical infrastructure for access and curation of data and provide a framework for describing your data using metadata standards. There are three different types of data repositories: institutional, discipline, and generalist. Institutional repositories are repositories that are provided by a particular institution for researchers at that institution. Disciplinary repositories like dbGaP or GEO for genomic data, they're targeted to certain types of data. And then you have generalist repositories. These are really available for any type of data, and you kind of use them as a third option. So typically you'll want to identify whether your funder has repositories that they want you to use. You can look into whether your institution already provides a repository. Maybe look into whether your discipline has a specific repository. And if none of those work, then you can use a generalist repository like Dataverse, Zenodo, or Figshare. So what do generalist repositories really offer, and what should you be looking for when selecting a repository? I've listed some advantageous characteristics there on the slide, including unique and persistent identifiers, so DOIs, essentially giving you credit for your data sets. Long-term sustainability of your data set to meet those grantor and funder requirements for data retention. They allow for metadata schemas. They help with data curation. Usually they're free to use, which is great. They have data security and access controls, which allow you to restrict or open access to your data sets. They also allow, again, for most data types and formats. And they support the concept of fair data, which we highlighted at the start of the presentation. One that I wanted to highlight real quick is Harvard Dataverse. It's a free web-based data repository. It's open to all researchers from any discipline. We do recommend that you utilize it here at Harvard. You can deposit up to 1 terabyte for free. I think you can deposit more than that if you actually talk to them, and they can work with you to deposit more data. And they are happy to consult on additional best practices for data publishing and stewardship and reusability of your data. I know we're running out of time, so I'm going to skip these couple, but I did want to highlight some data horror stories. This is our Halloween data management class today. So here are a couple of data horror stories that I actually pulled out. These are links that I'll be providing to you, so you can feel free to read all of the articles, but a couple of them are truly horrific, like NASA accidentally deleted data from tapes with original footage from their Apollo 11 moonwalk. They didn't, I guess, document which tapes actually had that information, and so someone actually erased them and reused them to record satellite data. Another one, a clerical error with the Social Security Administration accidentally designated a man dead while he was still alive, and they released his private information to the public, and he actually had to prove that he was still alive and get them to remove all that information from the internet. Microsoft Excel, the software actually removed 16,000 coronavirus cases. They went unreported because an outdated version of Excel limited the number of rows that were allowed and left off thousands of cases. And then the final one is particularly interesting. A Pixar employee accidentally started deleting all of the files for Toy Story 2. After it was already finished, right before it was supposed to be released, they pressed the wrong button on their keyboard. It started to delete all of the movie. They actually had to stop the deletion and go back and find an older version on someone's personal computer and bring that back to Pixar and actually finish the movie. So anyway, those are some horror stories today for your Halloween session, but feel free to read the rest of the articles after I give you the slides. So I'm going to stop the recording.